So anyway, yesterday I gave this introduction and they defined what open sets are. If you take a topological space, the members of the topological space are what are called open sets. Okay, so that's where we started off. So I'm just repeating the same thing, just that little bit, not too much. Xt uh, is a topological space, right? Uh, and the members of T are called open sets. I said many times I don't even write T extra. I just say X. X is the topological space. That's all I say. Okay, and then I say G is an open set. Uh, so G is an open set in T means the open set in topological space X. I might be a little reckless like that. It means G belong to T, where T is the underlying topology in X, where T is the underlying topology on X. And then I think last thing we did is that closed sets are introduced. That was the definition. This is already there in your notes. Okay, a subset. I mean, I have a topological space. Okay, a subset A of X is said to be closed if complement of A is open. Okay. So one actually easily notices that if you take a bunch of closed sets, their finite union is a closed set and arbitrary intersection is a closed set. Okay. So immediately we have noted the following. X, and this is all done yesterday already. X and phi are closed. That's because X complement is null set, that is open. Phi's complement X is open, and therefore X and phi are closed. That's the first observation. And the observation is that a arbitrary intersection of closed sets is closed set. Okay. Arbitrary intersection of closed sets is closed. Okay, you can see what happens if you take an arbitrary collection of closed sets, alpha and delta. Suppose are all closed. Okay, then X minus A alpha are all open. Are all open. And the arbitrary union of open sets is open, and therefore union X minus A alpha, alpha and delta is open. Okay, but that is actually X minus intersection A alpha. So this is open, and therefore intersection A alpha is closed. Therefore, intersection A alpha is closed. Okay, so arbitrary intersection is closed, but finite union of closed sets is closed, not arbitrary union. Second one is you can see that because these are the complements of open sets. That's why by De Morgan law I got it in the reverse here, right? So finite intersection of finite union of, I take it back. I think I said it wrong. Finite union of closed sets is closed. I think you can easily understand if AK is closed, for k equal to 1 to extra n, then x minus ak is open for k equal to 1 to n. Now, you see, finite intersection of open sets is open, therefore, intersection x minus ak equal to 1 to n. This is a finite intersection of open sets, and that is after all equal to x minus union ak equal to 1 to n. So, as these are finitely many open sets, their intersection is open, finite intersection is open. So this is open, therefore, union ak equal to 1 to n is closed. So that's what it is. So actually, the case of open sets, what I have is arbitrary unions of open sets is open, and finite intersection of open sets is open. But now closed sets, I have the complementation coming in. That's why arbitrary intersection of closed sets is closed, but only finite union of closed sets is closed. Okay, sir. Everybody okay with this? Can you hear me well?
Oh, yes, sir.
Yes, we can hear you. Okay.
Now we introduce the notion of a closure of a set. Okay, given any subset, so let X be a topological space. You know, many times if I don't say that, also you assume X is a topological space, right? I'm doing it all the time. Let X be a topological space. So we are minimizing our writing. I'm not writing XT is a topological space. I'm just writing X is a topological space. Later on, I won't even write that. Sorry for that. Okay. I just say whenever I write X, unless otherwise stated, X is a topological space. Okay. Let X be a topological space. For any subset A of X, I'm going to look at intersection of all closed sets which contain A. So intersection of all B, where B is a closed set in X and B contains A. Okay, I look at this intersection of all such B. Okay, please tell me. You have to reconnect it. Sure, go ahead. Okay, what happened? Oh, I see. So you have, okay. All right, please connect it. We have to restart everything, I think. Okay, please be on the line.
Okay, no problem.
Let A be a subset of X. Define closure of A to be the following: A bar to consist of all intersection of all closed sets B which contain A. B is closed and B contains A. Okay. So intersection of all closed sets that contain A is what we call the closure of that. So they are actually being approximated from above. All the closed sets, you look at their intersection all the way down, and that's that. Of course, as arbitrary intersection of closed sets is closed, this intersection is closed. So A bar is a closed set, and it contains A. So clearly you see that A bar is a closed set that contains A. Not only that, it's very easy to see that A bar is the smallest closed set that contains A. But if any closed set contains A, that is going to figure out in this collection, and the intersection is A bar. So immediately you make an observation that, so the observation is that note A bar is the smallest closed set that contains A. Okay. So that is a closed set is clear because it's the intersection of arbitrary collection of closed sets is closed. So A bar is closed. And A bar contains A because all of them contain A, their intersection also contains A. And why is this the smallest? I mean, If you take any other closed set that contains A, there is one member of the intersection, therefore the intersection will be contained in that. So that's what I mean by smallest closed set containing A. That is A is closed, A bar is closed, and if B is any closed set that contains A, that contains A, then A bar is contained in B. That's the sense in which I say A bar is the smallest closed set. A bar is a closed set, and every closed set that contains A contains A bar. Okay, so that's clearly what we have. And um, um, I might even, okay, then I'm going to write a little lemma. It's not a big thing. We can easily see what this is. Now, in a topological space, X, suppose I have taking sets A and B. A and B are subsets of X. Then here are the few things. What is the closure of empty set? Empty set is a closure set already. As a matter of fact, you can actually immediately prove. Uh, maybe I could just say that. Maybe I should just say that. Why not? You can just say that another observation is that a set is closed if and only if A bar is A. A bar is closed. If A bar is A will be closed. Okay. Okay. If A bar is A, then A is closed because A bar is closed. Conversely, if A is closed, oh, then A bar is contained in A because of the argument I just said. Okay. But A is contained in A bar too. So A bar equal to A. Right? If A is closed, okay, by the very definition, if A is closed and contains A, therefore A bar is contained in A. But A is contained in A bar, together A bar equal to A. So this is an obvious result. Okay. And now I prove the lemma. Okay. Let X be a topological space. And I'm gonna pick up two sets A and B. The following are two. Then one, closure of empty set is empty set, of course, because empty set is closed, its closure is itself. And closure of the whole space X is also X because X is a closed set, its closure is that. Okay. Two, A is contained in A bar. It's obvious. What I'm writing is not a big thing. A is contained in A bar. Okay. And A bar equal to A bar. A bar is closed. You just said that if a set is closed, its bar is itself. Okay. So if A bar is closed, bar is A bar. So at least for that reason, that is also over. And four, A union B whole bar is A bar union B bar. Why is that? Very simple. A bar and B bar are closed sets, so A bar, U bar, maybe I'll just prove the last one. First three are obvious. Okay, prove the last one. It's also nothing. If A bar and B bar, they are just closed sets, so their union is a closed set, and that contains A and B. So therefore, there's a closed set that contains A and B. So that contains A and B bar. First, one side is obvious. Let's prove that. Proof of 4. Okay. A bar, uh, A is contained in A bar, B is contained in A B bar. Therefore, A union B is contained in A bar union B bar, and the right hand side is a closed set, and A bar union B bar is a closed set. Oh, okay. That's a closed set that contains A and B, so that contains the closure of A and B. Therefore, A union B closure is contained in A bar union B bar. Okay. Conversely, I want to show that this is also very easy. Uh, you know, A is contained in A union B, and therefore you can easily say A bar is contained in A union B bar. So if any closed set that contains A union B contains A bar also, right? So intersection of all the closed sets that contain A union B, that is A union B bar, contains A. Okay. So A union B bar contains A bar. Okay. Right? Implies therefore this implies A is contained in B, therefore A bar is contained in A union B bar. And similarly, B is contained in A union B, therefore B bar is contained in A union B bar. And therefore A bar union B bar is contained in A union B whole bar. So I have the containment both ways. Okay, which means therefore A union B whole bar equal to A bar union B. As a matter of fact, I did something here. What I said is that if a set is contained in another one, its closure is contained in another. That's very easy to see. Because all the closed sets that contain A and B, their intersection is A and B bar. Okay, or maybe I can, right? Or maybe I can say, right, all the closed sets that contain A and B, they're all closed sets containing A and B, so their intersection is A and B bar. Okay, but they all contain A too. Okay, and more sets may contain, more closed sets may contain A, therefore A bar can contain A. Okay? So here is a little, not a corollary to that, and the small lemma, not a very big thing. So I can add a couple of things. If A is contained in B, then A bar is contained in B bar. Okay. Two, A intersection B bar is contained in A bar intersection B bar. Okay, now you will see slowly that you don't get equality here. For union, I get equality. I don't get equality here. I'll give you an example. That's why I enumerated. Even though they are quite easy things, I enumerated that for some reason. Okay. Everything else I wrote there, but I enumerated these four because these four can actually be taken as actions for something and create a topology from there. I'll come back to that. So I wrote only the four conditions, extra conditions I'm writing here. Okay. A intersection B whole bar is A bar intersection B bar. I will give you an example where equality does not hold. Okay. They are very easy proof. Okay. So A is contained in B. So every closed set that contains B also contains A. So the collection of closed sets in preparing the B bar are all there in preparation of the A bar, and even more may be there in the preparation of A. And that's it. That's why A bar is contained in B bar. If you don't like my arguments, you should tell me that. Okay. Every closed set that contains B, maybe I can say every closed set can perhaps C that contains B also contains A. Therefore, A bar is contained in C. Therefore, okay, a bar is contained in intersection of all C, where C is a closed set that contains C is closed and that contains B, and that is your B bar. So A bar is contained B. Okay, this is also very easy. You see, A bar is a closed set that contains A intersection B. B bar is a closed set that contains A intersection B. So A bar intersection B bar contains A intersection B. So that contains A intersection B bar. One side is done. Other side you don't get. I give you an example why you don't get other side. Okay. Oh, I see. Okay. Here's a example. Yeah, why don't you take the indiscrete topology? X is a non-empty set and with indiscrete topology. Okay, and topology is just the null set and the whole space. Okay, if you let's say X has enough elements, more than two elements are there. Okay, X is a non-empty set having at least two elements. Okay, having at least two elements. So I have set like this. I want to be able to choose two disjoint subsets. Okay, let A comma B subsets of X, A non-empty, B non-empty, and A intersection B is empty. Okay, I can always do that. I've taken some elements here, nothing in common between the two things. Then what is the A bar? A bar is the smallest closed set that contains A. Look, the only closed sets are empty set and X. And empty set doesn't contain A, only X has to contain A. So A bar as well as B bar are both X. A bar, A intersection B is null set. And therefore A intersection B bar is the closure of empty set, and that is empty set because empty set is already anyway, empty bar equal to empty set. And so what happened here? So A bar intersection B whole bar is only a null set which is contained in but not equal to A bar intersection B bar, that is X, which is A bar intersection B bar. So there it is. I don't get equality in the case of intersection. Okay. I would have asked you this also. Just leave it as it. And maybe I don't have enough examples yet right now. Very soon we'll introduce more examples of topologies, and then you can do this. I can ask you a question. Okay, even the following is also not true. Okay, so what is that I claim is not true? If A alpha be a subset of X for each alpha in delta, show that union A alpha in delta. See, for A union B bar, I proved A bar union B bar. This is only for finite. For something like this, show that this is not equal to union A alpha bar, alpha belongs to delta in general. That means I can create a counterexample where this theorem doesn't work for arbitrary unions. Okay? Here is a theorem. Closure, that's something that hugs A very neatly. So a point will be in the closure. Maybe I can give you a little definition also. This is actually a useful definition. Let X belong to X. Any open set that contains X is called a neighborhood of X. Okay. Any by neighborhood of X, we mean any open set that contains X. Okay. By a neighborhood of X, we mean any open set that contains X. Any open set containing X is what they call a neighborhood. Okay. So here is a little a theorem. Okay. Let X be a topological space. And A be a subset of X. We're going to give you a criterion for a point X to belong to A bar. Then X belongs to A bar if and only if for every neighborhood G of X, that means every open set G that contains X, if and only if for every neighborhood G of X, okay, G intersection A minus singleton X is non-empty. Okay. Intersection A is non-empty. That's all. Okay. What is that? So that's what it is. It's with the closure. Every neighborhood G of X is going to have a non-empty intersection with the set A. That's when X is in G bar. It's very easy to prove. Yeah, one side probably, yeah. Okay, if X is in A bar, you want to show that and take any open set containing, select X belong to A bar and let G be a neighborhood of X. That means G is an open set, it contains X. You want to show that G intersection A is non-empty? Well, I think it's very easy. If G intersection A is empty, okay, I don't want to show it's non-empty. If it's empty, then you know, A is contained in X minus G. Right? A is outside G. But that's a closed set. And X minus G is closed. This is contained in the closed set, so its closure is contained in X minus G. Hence, A bar is contained in X minus G. Oh no, that which implies that even G intersection A bar is also empty. A bar intersection G is empty. Now that's a problem because you already said X is in A bar and G is a neighborhood of X. So G contains X as well as A contains X. How can this be non-empty? A contradiction? Not a contradiction. It's not possible. Not possible. Why? Because X is in because X is in A bar intersection G. Okay. So if X is in A bar, if we take any open set G containing X, that is a neighborhood of X, G intersection A must be non-empty. Why? Because if it is empty, if it is empty, G intersection A is empty means A is inside the outside of G. And that's a closed set. A is contained in the closed set means its closure is contained in that. And A bar is outside G, that means A bar intersection G is empty. But X has A is in A bar and G also has X. X is in both of them. We can't say it's empty. So that's a contradiction, therefore. Okay. And therefore, G is a contradiction. Okay. So G intersection A must be 9. This proves the first part. Hence, G intersection A must be 9. Conversely, suppose the condition is holding. Conversely, suppose, okay, G intersection A is empty, non-empty for every neighborhood G of X. So I have to show that X is in A bar. Okay, I have to show that X is in A bar. Okay. How do you show that X is in A bar? Oh, I think the same kind of an argument can be given. How do you show that X is in A bar? Well, I want to show that we wish to show X is in A bar. Suppose X is not in A bar. Suppose X is not in A bar. That is, X is in X minus A bar. Okay, X is not in A bar means X is in X minus A bar. Okay, that means, oh, I can take this as a G, I get into trouble. This is an open set. Okay, so if you call this H, H is an open set. And X is in H. I think I went round and round. I should have. X is in H. Now H intersection A should be non-empty. Now that's not possible. Okay, condition is there, right? Therefore, H intersection A should be non-empty, but that's not possible. H is no, H is outside of A bar. Okay, but that's not possible because okay, that's not good. Okay, so what is that? Why is that not good? Empty set is non-empty. H intersection A. H intersection A is contained in H intersection A bar. A is contained in that. H intersection A bar is X minus A bar intersection A bar, and that is empty. There sits the contradiction. A contradiction. Okay. So an element is in the closure if and only if every neighborhood of G intersects that set A. That's what I prove. Okay. I hope. Any questions there, sir? Are you good with that? Right? Okay. Express. We give you a definition of a limit point. Actually, I'm going to characterize the points of a bar. Some of them will be limit points. Limit point means, if anybody who has an idea about sequential compactness and so on, you will see that I want something to approximate some points here. That's what limit point is. So limit point means that if you take any neighborhood of that, okay, that should contain some points of A other than this X. Okay, so let A be a subset of X. A point X in X is called a limit point of A if for every open set that contains X, G intersection A minus X, if and only if for every open set containing it, or we can say for every neighborhood G of X, G intersection A minus singleton X is non-empty. That's when you say that point is a limit point. I'll give you enough examples. First of all, I have not given you enough topologies. I've given you about four topologies in aesthetics, right? Once we introduce the idea of a base of a topology, we'll tell you how to generate lots of topologies. Well, let's wait. It's not a big deal if I don't have given you too many examples. Okay. So for every in the real line, you understand these things. I mean, we did talk about all these things when we did complex analysis, but as it is in this course, also I'll give you plenty of examples. So for every neighborhood G of X, G intersection A minus singleton X is non-empty. That is when I say that X is a limit point of that. Okay, I can talk about an isolated point also. In the set A, suppose this may be the set A. How is this set A, including this point? This point is isolated in the sense that I can squeeze in a neighborhood around that point X, which has no other point in intersection with A. That alone is the point that is inside G, and no other point. That is how we say isolated point is there. Somebody just sitting isolated. So A is what? A is along with this set and this element together is the A. Suppose all these things together is A. And what sort of a point is this? It has a neighborhood in the complex plane. I see these things clearly. It has a neighborhood. That means an open set that contains that point whose intersection A is when empty. That is when I say that point is an isolated point. A point is the definition of isolated point. Okay. Let A be a subset of X. Okay. A point small x of A is called an isolated point of A. If there exists a neighborhood G of X such that G intersection A has only that element, nothing else. Okay, G intersection A is just that singleton element and nothing else. So that point is isolated. Right. Actually, neighborhoods are like the neighborhoods you have in the real life, in the real space. What is the neighborhood? Little portion around you. Even though you have taken an open set containing that, actually, when you talk about the topology and the Euclidean plane, you see that the topology is what everybody would actually imagine. Your neighborhood is some portion around you. Here I am at some place in Visakhapatnam. Okay, what is my neighborhood? Just draw a small circle around me. That is the neighborhood. So any open set that is around me sort of imitates, okay, a small circle around me. Or maybe it doesn't have to be a circle. It can be a big blotch of things. For example, if I am here in Visakhapatnam, right? When maybe I'm just a little bit under the land. But however, if I say neighborhood, what is the neighborhood? This is the neighborhood. This is not the entire land. Some sea is also there. Or otherwise, if you don't want to talk about that portion, what is my neighborhood? Neighborhood is some lopsided thing like that. Doesn't matter. So when an open set containing X is imitating a certain region around me, a certain patch around me, which looks like a little circular patch or even other patch, doesn't matter. We will understand all these things as we do more, give examples of more topologies, which we'll do in soon. So what is an isolated point of a set A? Here is an element of A, but somehow it's sitting ideally away from the rest of them, that there is a neighborhood I'm able to find out a G around X, so the G intersection A has only that element, nothing else is there. Around that patch around X, there is nothing of A in that. Then I say that X is an isolated point of A. Limit point means it's such that every neighborhood of that point X has to have an intersection with A. Apart from X, I have something more into it. Okay? I hope you're okay with that. Okay. So notice, given any set, a subset A of X. If something is an isolated point, there's not a limit point. If something is a limit point, there's not an isolated point. So every point of it is either a limit point or an isolated point, but it's not both. Okay, every point of A is either an isolated point of A or a limit point of A. Okay, but not both. Of course, there may be some points outside A which can be limit points too. But as far as isolated points, I'm talking about the points of A only are isolated or not. They're isolated if every neighborhood, if there is a neighborhood around that point whose intersection A with will be only that element and nothing else. Okay. Now the set of all limit points, we have used this notation before in complex analysis course too. So here is the notation or definition. I may call that a derived set. Okay, given a subset A of X. Okay, the set of all limit points of A is called the derived set. The set of all limit points of A is called the derived set of A. The derived set of A, and is denoted by the A. Okay, so that is what a derived set of A is. It is an important theorem that I want to talk about, which is a little theorem. Given any subset A of a topological space, the closure of the set will be A union the derived set. If all the limit points go back sit in A, then go back and sit. They will always inside the A bar. Okay, for any subset A of X, A bar is A union D of A. Let's prove that. Okay. First of all, A is contained in A bar. If I saw dA is contained in A bar also, then A in dA will be contained in A bar. Okay. A is contained in A bar. I want to show that dA is contained in A bar. So take any element X of dA. That means it's a limit point of that. Therefore, for every open set that contains X, that G intersection A minus single, then that should be non-empty. Okay. Right? Very good. Yeah, I think this is just very simple. Then for every neighborhood G of X, G intersection A minus singleton X is non-empty. That is because X is a limit point. But then G intersection A is also non-empty. Hence, G intersection A is non-empty. Therefore, X is in the bar. So thus, even dA is a contained in A bar. A is contained in A bar, D is contained in A bar. Therefore, A union dA is contained in A bar. Conversely, I want to show that A bar is contained in A. Let's talk about that. To prove A bar is contained in A, I'm going to take an element X in A bar. Okay. To prove A bar is contained in A union dA. Okay. Take any X in A bar. X may be in A. You are fine in that case. If X is not in A, then what happens? Okay. Take any X in A bar. I want to prove that X is in A union dA, right? Okay. For any neighborhood G of X, it is an A bar means G intersection A is non-empty, right? It's an A bar. So G intersection A is non-empty. That X may be in A. If it is not in A, right? So X is in A. Yeah, that's good. If X is in A, we are fine. If not, okay, if X is in A, we are fine. I'm trying to show that A is contained, A bar is contained in that. I took an X in A bar. If it is in A, that's fine. If it's not, I'll see. If suppose X is not in A. Anyway, X is in the closure, therefore every neighborhood of G has this G intersection A is non-empty. But now, G intersection A is non-empty. So G is empty for any neighborhood G of X. What is that? X is in A bar, right? G intersection A is non-empty. Okay, fine. So hence G intersection A, X is anyway not there in A. So X is not in the intersection. So this minus this is also non-empty. Oh, therefore X has to be limit point. Okay. Therefore X is in B. Yeah, I was not thinking properly. It's very obvious. Sir, any questions about this argument? So you have no other option. So A bar, therefore A bar is contained in A union B. So given in A, what we are doing is that not only picking up all the elements in A, if there are any limit points, they are also picked up into the closure. The closure will be there. Even I have not taught you enough of the topologies, but in real life, in complex plane, if you look at an open disk, if you take an open disk, including the boundary will be along disk and the boundary will be the closure. That's what this union DA will be. Okay? This completes the proof. So immediately I have a kind of a corollary that you can understand right away. See, for example, if A is a closed set, A bar is A. Fine. A is a closed set, so A bar is A. So then what happens? If A bar is A, the DA is subsumed in that. So I think DA should be subset of A. So immediately I have a corollary, right? If A is a closed set, A bar is A. What do you mean by A bar is A? Then DA should be subset of A bar. That means DA is a subset of A. So if A is a closed set, DA is a subset of A. And indeed, that becomes the condition. A set will be closed if DA is contained in A. That can immediately prove this corollary. A subset A of a topological space X is closed if and only if DA is contained in A. What happens is if DA is contained in A, DA in A is A only and there is A bar. So A is closed. The A will be A bar. And in case A is closed, A is A bar, then where is DA? DA has to be in A bar, and that is in A. So I think this is nothing. Just logically, it falls apart. That a subset A of a topological space is closed if and only if all the limit points of that are back in A. Okay? I think these are all fine there. I'll just introduce what is called a boundary, and maybe I will postpone the rest of the stuff for tomorrow. Here is the definition of a boundary. Given in a set A is a subset of a topological space, if A given a subset, given a subset A of a topological space capital X, we define its boundary of A to be, it is the set boundary of A is actually the closure of A intersection is the closure of the complement. Okay, so here is the subset A. Its closure and its closure, their complements closure, their intersection is what I call the boundary field. We'll talk about more about this in due course of time. Okay. Therefore, here is a simple theorem. X belongs to boundary of A when it's in the closure of A as well as in the closure of A complement. So if you take any neighborhood of X, it is in the closure of A, therefore that neighborhood intersection A is non-empty. It's the closure of the complement also, therefore that neighborhood of neighborhood intersection A complement is also non-empty. So any neighborhood of X, if X is in the boundary, any neighborhood of X in open set containing X will intersect both A and in A complement. So X belongs to boundary of A if and only if for every neighborhood G of X, both G intersection A is non-empty and G intersection A complement is also non-empty. Just it's on the boundary. I think it makes sense that the definition of the boundary is all very nice here, right? Okay. Here is a little theorem that I do regarding the closed sets. It's very, very obvious. If I have open sets, that is, I have a topology, I have the subsets of all the elements of the topology are the open sets and their complements are closed sets. I have shown you that the closed sets satisfy a couple of conditions. What are three conditions they satisfy? Namely, empty set X is closed and arbitrary intersection of closed sets is closed and a finite union of closed sets is closed. You know what? If you take any collection of subsets of X, which has all these three properties, then if I take any collection C of subsets of X which satisfies all these properties, then the collection of all complements of the sets of the given collection, they form a topology. It's very easy to see that. Let X be a non-empty set. Just a non-empty set. I'm not saying there is any topology on it. Just a set. I'm going to create a topology on it. Okay. If C is a collection of subsets of X, if C is a collection of subsets of X, okay, I'm going to go 5 minutes. Is that okay for everybody? Just 5 minutes. Huh?
Yep.
Yeah. Let C be a collection of subsets of X that satisfy one, null set and the whole space are in C, and two, C is closed under arbitrary intersections. And C is closed under finite unions. Then T, which consists of all the complements of C. That means G is in T when if its complement is in C. Then T is a topology NX. Does it make sense or not? Okay. What happens? There are the complements of the members of this. So if you look at an arbitrary union of sets in this, their arbitrary union of such X minus GKs. Okay. But the arbitrary union of X minus GKs is in C. Okay. Which means X minus arbitrary. Okay, I will write that. It's not a big thing. T is a topology is quite obvious, right? What happens if you take an arbitrary collection of G's, you take an arbitrary union. Arbitrary union is the intersection of the arbitrary complements there. And the intersection of arbitrary complements, they're all in C, therefore that is in C, etc., etc. So here, I'll just finish it off right here. So if you take, first of all, These two are in C, and because this is in C, X is in G, X is in T, and because X is in C, empty set is in T. Okay, so X empty set is in C implies X is in T. Uh, whole space is in C implies empty set is in T. So T has contained both the null set and the whole space are in T. Okay, if G alpha belongs to delta, some indexing said, if it is a collection of it's a subcollection of T. Okay, then what is this X minus G alpha in delta becomes a subcollection of C. But C is somehow closed under arbitrary intersection. Therefore, the arbitrary intersection X minus G alpha in delta, this is going to go sit in C. But this, after all, is X minus arbitrary union of G alphas. And that is in C. Therefore, this union G alpha in delta is in T. So you see that T is closed under arbitrary union. Where you can prove that T is closed under finite intersections. Okay, here is the proof going on. Okay, so I'll complete this sentence. So T is a topology on X whose closure sets are precisely the members of C. Is that clear for everybody? There is nothing in there. Okay, I just have to keep writing the proof if it's necessary. I can leave it there. So work out the details if you really think it is necessary. And here is what I want to write down a little theorem. Krotowski's actions. Actually, Krotowski was one of the people who had done a great deal of things in topology. Okay, he introduced topology in a slightly different way. From the closure, okay, you can look at the closure of a set. It has certain properties it satisfies. Empty set closure is empty set, X closure is X, and A is maintained in A closure. A closure is A closure, and A in B closure is equal to A closure union B closure. These are the properties there are. And you see what this theorem really says. It says that, okay, let X be a non-empty set. Oh, suddenly the color has changed. Huh? Why is that? Okay, be a non-empty set. Okay, and I'm going to have a function C, and the map C, which maps the elements of the power set of X back into the elements of the power set of X, satisfies the following. C of null set is null set. C of full space is itself. And every subset of A, X, is contained in its A. And C of CA is CA. And finally, C of A union B is CA union CB. If these conditions are satisfied by C, the C can create a topology. You can already guess it. Okay, all right. C will create a topology. Topology is what? Actually, C will first of all create this set C consisting of all those A such that CA equal to A. And I want these things to be closed sets. And therefore, the topology is complements of all such things G such that X minus G is in C. And we will notice that this T will be a topology. Okay, right? Then Very good. Let C be the class of all elements of the power set of X for which CA equal to A. Then you can show that this C satisfies the hypothesis of the previous theorem. Then, okay, empty set and X are in C, and C is closed under arbitrary intersections and finite unions. We can easily prove that. Okay, finite unions, and therefore, T consists also G such that X minus G in C is a topology on X. So this is exactly how Protosky has introduced topology. Okay, so I hope you can realize that this is nothing big deal. Okay, so you just have to prove this, that this collection satisfies. This is just follows from the properties very easily. You can prove that this happens. Okay. So this is what I wanted to say. Of course, we are not going to go through this line of things, just to demonstrate that there are other ways of defining topology. I have done this because it's one of the early definitions given by Protosky, right? So, for example, you can say C empty set is empty set Cx is equal to X. So, empty set and X are in C already. Okay. That part is there. So, what you have to prove is that arbitrary intersection of sets in C is back in C. You have to prove that somehow or other. So, maybe if you want to think about it, you look at the details and we'll come back to this. I'll stop the lecture here. Okay. Right. Yeah, you can actually start. So actually in the next class, I'll introduce base for some topology, and I will have an opportunity to introduce plenty of, oh, I have to introduce interior also. I will have an opportunity to introduce a lot of topologies. Okay, that's all for now. And if you have any questions, you are welcome to ask. Okay.
It's good. Thank you.
Thank you, sir.
That's all. So again, we'll see you on Friday. Okay. Okay.
Thank you. Bye.
That's it.